Hello friends, I welcome you in lecture number 28 on relations. In this lecture we are going to discuss properties of relations using relation matrix. In lecture number 27 we have discussed what is relation matrix and how to write down the relation matrix corresponding to given relation. So if you have not seen lecture number 27, I suggest you to watch that lecture first and then go for this lecture. Now suppose we are considering relation on a set. Suppose R is a relation on a set A, then R is a subset of A cross A, or R is a relation from set A to itself. So whenever we have relation which is defined on a given set, then we can decide some properties of that relation using its relation matrix. And suppose we have this set A whose number of elements in this set A are say n, then relation matrix will be a square matrix. If we have relation from set A to itself, and if there are n elements in a given set A, then its relation matrix is a square matrix of order n, or it is an n by n matrix. Now using that relation matrix we can decide the properties of that relation, and that we are going to discuss in this lecture. For example, suppose we consider set A having two elements, say 1 and 2, and we consider some relation R on this set. So R is a subset of A cross A. Suppose I consider these two elements 1 1 and 2 2 and say 1 comma 2, then it is clear that this relation R is reflexive because it contains this type of diagonal elements. For every element in a given set we have this type of elements present in our relation. So this relation is reflexive relation on this set A, and this set has two elements, therefore its relation matrix will have order 2, or it will be a square matrix of order 2. Now to write down the relation matrix, we first consider this type of table as we have discussed in last lecture. Here we write down 1 and 2, here also we write down 1 2, because we have a relation from set A to itself. Now we concentrate on all the possible pairs. First we fix 1, and we have 1 comma 1, and order pair 1 1 is present in this relation, so here we write down 1. Then order pair 1 2, it is also present, so here we write 1. And then order pair 2 1, it is not present in given relation, so we write 0 here. Order pair 2 2 is present, so here we write 1. And the relation matrix is a square matrix of order 2, and these are the entries of relation matrix corresponding to this relation. Now if you observe that these main diagonal entries are 1, and this is obvious because whenever we have reflexive relation, we will always have this type of diagonal elements present in our relation. So if relation is reflexive, then relation matrix is having this property: all the entries on the main diagonal are 1, and this is true for every relation R on a set A which is reflexive. If relation R is reflexive, then all the entries on the main diagonal of a relation matrix are always 1. So using this property we can decide whether our relation is reflexive or not, even if we don't know the relation, and from matrix itself we can say that whether this relation is reflexive or not. So that is the first property which we can decide from relation matrix. If all the entries on the main diagonal of a relation matrix are 1, then relation is reflexive. So here I have written, if a relation is reflexive, then all the diagonal entries must be 1. In other words, if there is at least one diagonal entry which is 0, then relation is not reflexive. Now similarly we can check symmetry property also. For example, here I can write down this symmetric relation on the same set. For example, suppose I want to construct a symmetric relation on this set A, then here I have written 1 2, so I have to add 2 1 also. So now this relation is symmetric also on the same set. So here my relation matrix will also change. I will have different entries now. Here 1 1 is present, so I am writing 1. 1 2 is also present, so here also I write 1. 2 1 is also present and 2 2 is also present. So this relation is symmetric relation and we have written its relation matrix. Similarly, we can construct another symmetric matrix also. For example, suppose I consider S equal to say 2 2 and 1 2 and 2 1, then this is clearly symmetric. And if we write down the matrix corresponding to this, then 1 1 is absent, so here I write 0. 1 2 is present, I should write 2 here. 2 1 is present and 2 2 is also present. And let me write another symmetric relation also. T equal to say 1 1 only, then relation matrix corresponding to this relation T, let me write down the matrix corresponding to this. So we have only one order pair present, so here we have 1 and other entries are 0. So here you can see I have written or constructed 3 symmetric relations on the given set A. Now what is the characteristic of all these relation matrices corresponding to this relation given relations which are symmetric? So if you observe that entries are symmetric with respect to main diagonal, I have drawn this main diagonal, and if I consider perpendicular lines here, then you can see entries are symmetric with respect to main diagonal. Here I have 1, so here I have 1. If I have 0 here, then I am having 0 here. And if you are familiar with the definition of symmetric matrix, we know that a matrix M is symmetric if its transpose is matrix itself. For example, if I consider this matrix 1 1 1 1, and if I take transpose of this matrix, then I will obtain this same matrix. Therefore this relation matrix is a symmetric matrix. Same thing here matrix is 0 1 1 1, and if I take the transpose, then I will write down first row as first column, second row as second column, and you can see I get the same matrix. And here also we can find out the transpose 1 0 0 0. If I take transpose here, I have 1 0 0 0. So if our relation is symmetric, then the relation matrix corresponding to that relation is also symmetric. Therefore, from the relation matrix itself, we can decide whether given relation is symmetric or not. We have to find out the transpose of relation matrix, and if we obtain the relation matrix as its transpose, then relation matrix is symmetric and therefore given relation is also symmetric. Or we can check whether entries are symmetric with respect to main diagonal or not. For example, this entry is in first row and second column, so I have m12 equal to 1, and if I change the order here, then I have m21, so m21 is also 1. So in general, if our relation is symmetric, then relation matrix satisfies this property. ijth entry of relation matrix and jith entry of relation matrix are always same if I and j are different, and we don't have to worry about diagonal entries. They can be either 0 or 1. So this is the second property which we can decide from the relation matrix. If a relation is symmetric, then the relation matrix is also symmetric, that is, transpose of relation matrix is relation matrix itself. And last one is antisymmetric property. Antisymmetry means if order pair AB and order pair BA both are present in a given relation, then A and B cannot be different. In other words, if A and B are different, then either AB is present or BA is present in a given relation. So in that case, we can see, for example, if I want to make this symmetric, then I have to remove one pair. Same thing here, if I want to make this symmetric, let me remove this pair. Don't worry about diagonal elements. And we can observe the change in the relation matrices. Let me write down the relation matrices corresponding to this R and S which I have modified. In R I have 1 1 present, then 2 2 present and 1 2 present, and remaining entries are 0. In S I have 2 2 present and 2 1 present, remaining entries are 0. So if our relation is antisymmetric, then we can see that these two entries are opposite. Opposite means if I have 1 here, here I have 0. This entry is nothing but entry in first row and second column, and this is entry in second row and first column. If m12 equal to 0, then m12 equal to 1, then m21 is 0. Same thing here. Here m12 is 0 and m21 is 1. So if our relation is antisymmetric, then relation matrix satisfies this property. If ijth entry is 1, then jith entry must be 0, and vice versa. If this entry is 0, then this entry must be 1 if I and j are distinct or different. If a relation is antisymmetric, then its matrix is such that if mij equal to 1, then mji equal to 0 for I not equal to j. So remember these properties, very easy to observe and decide properties of a relation. If all the diagonal entries are 1, then relation is reflexive, otherwise it is not reflexive. If relation is symmetric, then relation matrix is also symmetric, that is, entries are symmetric with respect to main diagonal. If relation is antisymmetric, then its matrix is such that if ijth entry is 1, then jith entry must be 0, or if ijth entry is 0, then jith entry must be 1. So let's do one exercise to decide whether given relation satisfies certain properties using its relation matrix. Here we are given the relation matrix of a relation R, and we have to decide whether this relation is reflexive, symmetric or antisymmetric. So for reflexive property, we will concentrate on the main diagonal, and you can see here all the entries on the main diagonal are 1. Therefore this relation is reflexive. So I can write here that all the diagonal entries or all the entries on the main diagonal, all the entries on the main diagonal of a relation matrix M are 1. Therefore, relation R is reflexive relation. For symmetry property, I have to check whether these entries are symmetric with respect to main diagonal. I have to check this. So you can see here entries are symmetric with respect to main diagonal. If I have 1 here, here also I am having 1, 0, then 0, 1, then 1. Or we can observe in this way also. If we find out the transpose of this relation matrix, then let's see what happens. I have to write first row as first column, second row as second column, and third row as third column, and you can see we obtain this as relation matrix. Transpose of relation matrix is relation matrix itself. That means relation matrix is symmetric and therefore given relation is symmetric. So we can write that here transpose of relation matrix is relation matrix itself. This means relation matrix is symmetric and therefore given relation R is also symmetric. And now I have to check whether given relation is antisymmetric or not. So for antisymmetric, we have to check that if ijth entry is 1, then jith entry must be 0 whenever I and j are different. For example, I consider these two entries M12 and 21. M12 means first row and second column, and here we obtain 1. And M21 means second row first column, so here also I have 1. And if relation is antisymmetric, then if this is 1, this must be 0. So this relation is not antisymmetric. Same thing here also we can see A13 is 0 and A31 is not 1, or these two must be opposite of each other. So this relation is not antisymmetric. So we can write that here entry M12 and M21 both are equal. M12 equal to 1 and this is equal to M21. Therefore, R is not an antisymmetric matrix. So in this way we can check whether given relation satisfies certain properties using its relation matrix and without writing the relation corresponding to that matrix. And therefore you can see in this exercise nothing is given related to the set on which this relation is defined. We are given the relation matrix only. We are not given that on which set this relation matrix, on which set the relation corresponding to this relation matrix is defined. So whenever we are not given relation R and the set on which it is defined, and we are just given relation matrix, then also we can decide certain properties of given relation. So this is all about this session. We will continue in this series in upcoming lectures. Thanks for watching.